Okay, so how can we use this idea of a block design to aid us in this study about SAT improvement scores with an online course versus an in-class course? All right, so first, let's break it down and talk about how we would do the experiment if we had these 20 kids. So let's suppose from these 20 kids that 10 of them were in pre-calc, 6 were in algebra 2, and 4 were in geometry. It should kind of make sense that maybe on these courses would um, react differently to kids in different classes. Well, here's what I think. Like in pre-calc, those kids don't have much to learn. Like they've done most of the material. So maybe these classes aren't very effective for pre-calc kids, but if you're a geometry kid, maybe it'll be very effective because maybe you haven't done trigonometry or something. Okay. Regardless, the question is, if we break them into these groups, can we reduce the variability and somehow maybe see differences? Because up here, we weren't really able to see any significant difference. So how do we do the how would we do this? Well, let's take our 20 kids, and this is not random. First thing we're going to do is break them into groups. We got our 10 pre-calc kids, our 6 algebra 2 kids, excuse me, and our 4 geometry kids. This is not done randomly. I don't randomly group them into these blocks. These are our blocks. Okay? Now we're going to do our random assignment. So I'm going to randomly assign half of the pre-calc kids to go into the online, take that course, take the SAT, half of them to go into the classroom. Here it's going to be 3 online. Ugh, I don't like 3. 3 is getting pretty small. We're losing our replication, and this is actually going to be 2. This is a disadvantage of blocking. You're going to lose some of your power, if you will, uh, by reducing your size in each of these groups. But hopefully, what we get back by reducing this variability because of these blocks will make it worthwhile. So then we are just going to compare these two. We're going to compare their SAT improvements. And then with these two groups of kids, we're going to compare independently. It's almost like we're going to do 3 separate analyses rather than just one comparison at the end. And then we can kind of look for our overall conclusions. And you never know what it's going to be. Maybe, in geometry, maybe for these kids online was better, and for pre-calc kids class was better, and for geometry it doesn't matter, or who knows how this is going to work out. But that's how randomized block design is set up. All right, so let's look back at our example with the SAT. I didn't give you this information before, but suppose these kids who had these scores were pre-calc kids, and these kids were algebra 2 kids, and these were geometry kids. This is just made up information. In fact, it looks like the improvement scores for pre-calc kids was more than for geometry. In reality, you probably would see these kids improve more because they have more room for improvement on their math if they take a course. And these might actually be less. Whatever, it's made up data. So if we plot those and look at the courses that they took, so in this dot plot, we have the same dot plot, only we're using symbols and colors for different groups. So here's the 2 geometry kids that were in the class, and here's the 2 online geometry kids. And as you can see, the online kids did kind of score higher than the other 2. Now, I'd be very wary about making any conclusions here because it's only 2 kids. That could have been due to random assignment. We're losing out replication here, but it looks like there's an improvement. And then for algebra 2, these are the algebra 2 results for classroom, and these are the algebra 2 results for online. Again, and maybe we got not a big sample size again. I don't know if that's a significant difference, but what it does is it really reduces the variability within the groups. In the original, I had all this variability, scores from 100 to 20 in both groups. But now, because I block by class, and actually in this one here is probably the most, I have the biggest, I got the most replication here, so I got these big groups. It really kind of gives me a sense of the amount of spread, and it looks like maybe we could find a significant difference between those two groups. So by blocking, we're able to reduce the variability in each of the blocks and then maybe draw more powerful conclusions. All right, so hopefully this kind of illustrates the advantage of blocking, but also the disadvantages of blocking. The main disadvantage of blocking is you lower your replication, and by lowering your replication makes it a little harder to see significant differences. But usually the advantage that you get by reducing the variability is well worth it. So blocking in experiments is similar to stratification in sampling. Blocking accounts for a source of variability just like stratifying. This means that blocking is a good way to increase your chances of detecting a significant difference. Blocks should be chosen like strata. The units within the block should be similar, but different than the units in other blocks. That's why we block by, these kids are all similar. These kids are all similar by math level anyway. I mean, they're not similar by gender or any other value, but so we are, we're just blocking on one variable. You should only block when you expect that the blocking variable is associated with the response variable. For example, in this problem here, we could have blocked by gender. But would it have made sense to block by gender? The only time it would have made sense to block by gender if you had some reason to believe that online courses versus classroom courses might affect guys and girls differently. Or block by, you can pick a variable, right? And then what you're going to do is you're going to evaluate all those. I got gender, I got ethnicity, I got socioeconomic status, I got height, I got hair color, and I got math class. Then you decide which one of those is going to influence your, are the treatments going to influence the most with respect to what the response is? And then the one that you should block with is the one that is most highly associated, okay? Blocks are not formed at random. Statistical advantage of blocking. Blocking accounts for a known source of variability in the response variable. The reduction of variability within the blocks allows for a more precise comparison of the treatment groups. We have a better chance of detecting differences in the response variable and attributing those differences to the explanatory variable. Okay, it's a lot of words. I think I added this to the notes because this came up. Kids who were on the AP test were asked to talk about the statistical advantage of blocking. So, put a star by it. I don't want you to memorize these types of things, but, try to understand them, I guess. Why are the pages off center there? It's weird. Okay. What are some variables that we can block for in the caffeine experiment? You can block for anything you want. Maybe gender, body size. You got big kids. You got relatively small or body size. I mean, like weight, I guess. Caffeine habits. If some kids drink a lot of Starbucks and have caffeine every single day, maybe they build up an immunity to caffeine. Whereas if other people don't drink any caffeine or any sodas, they might react differently to caffeine. So that might be a sensible blocking variable. Athletes, non-athletes, maybe. Let's pick something that we don't think is going to have any influence on it at all. Whether you like dogs or cats. I don't think that has anything to do with. So, you can pick variables that make sense. You can pick variables that don't make sense. Who knows, right? You can pick any variable you want. In general, how can we determine which variables might be the best for blocking? Well, we're going to pick the variables that we think are going to have the greatest how the explanatory variable of caffeine is going to interact across the response variable, which is heart rate. So we want to, obviously this is a nonsense one, right? This is not going to influence how you react to caffeine, nor impact your response of the heart rate. But this one might, because you might react differently to the caffeine, and your heart rate may be different because of that different reaction to the caffeine. Gender, I probably wouldn't say as much. Body size, maybe. If you're really big compared to really small, you might have a more of an influence because of how much caffeine you take. I would probably say this is the most important one. This was another one that I don't think would really have much to do. But maybe athletes' heart rates are maybe less influenced by drugs. Who knows? The best variables to block for are the ones that best predict the response variable or are strongly associated with the response variable. Okay. Sound experimental design means controlling as many variables as you can, utilizing blocking on the variables you can't control that may significantly impact the response variable, and utilizing randomization and replication to balance out the effects of the variables you can't control. Replication will also ensure that we have a better chance of detecting significant differences. Okay, this is a nice little summary of the entire unit that we've done so far. And if you understand it, you're sitting good. Match pairs design. So there is another form of blocking called a match pairs design. And I think this is the last topic, kind of. Oh my gosh. Okay. I'm going to start a new video at this section here. So check out the next video if you want to learn about a match pairs design.